Hello and welcome. Today we're diving into the incredible world of organic chemistry. We're going to explore the amazing science of carbon. The element that's literally the foundation of life itself. From your DNA to the food on your plate and even the medicines that keep us healthy, it's all about carbon.
All right, so let's get right to it with the big question, right? Think about it. There are over 100 elements out there. So why on earth does just one of them, carbon, get its very own massive branch of chemistry all to itself? The answer to that is the key to unlocking this entire topic.
So here's how we're going to break it all down. First, we'll look at what makes carbon so special, its unique talents. Then, we'll learn the language chemists use to actually draw and name all the cool things it builds. After that, we'll see how these molecules interact, how the reactions happen. And finally, we'll take a peek into a chemist's toolkit to see how they handle these molecules in the lab.
Okay, let's jump right in. What is carbon's big secret? Well, it all boils down to a few really incredible properties. These are the things that let it become the backbone for literally millions and millions of different compounds.
So first up, we have something called tetravalence. I know, it sounds a bit technical, but all it really means is that a single carbon atom can form 4 super strong, stable connections. These are called covalent bonds. Just imagine a tiny building block with 4 connection points. It's just perfect for building these huge, complex, three-dimensional structures.
But here's carbon's real superpower. It's called catenation. See, other elements might be able to link up with themselves a couple of times, but carbon is a total pro at it. It forms these incredibly long, stable chains and even intricate rings. And this ability to create these massive molecular skeletons, that's exactly why the number of organic molecules out there is pretty much endless.
Now, these bonds don't just form randomly. They create very specific 3D shapes. The way they do this is through a process called hybridization. So if a carbon has all single bonds, which we call sp3, it makes this cool 3D pyramid shape. If it has a double bond, or sp2, it goes flat, like a triangle. And with the triple bond, an sp, it just forms a straight line. And trust me, this shape is everything. It dictates how a molecule fits, how it behaves, and how it's going to react. All right, so we've established that carbon is basically a master architect. Now, let's get into the language chemists invented to actually draw and name the countless structures it builds. It's really like learning a whole new alphabet and grammar system. So, one way to do it is with what's called a complete formula. As you can see, you draw out every single atom and every single bond. It's super clear, no doubt about it. But you can probably imagine if you had a really big molecule, this would get incredibly messy really fast. So, to clean things up, chemists often use a condensed formula. All you do here is group the hydrogen atoms with the carbon atom they're attached to. See? It's the exact same information, just packed into a much neater, tidier format. Okay, but the way you'll see it most often is the bond line formula. This little shorthand is an absolute game changer. It's so elegant. Every corner and every end of a line represents a carbon atom. And we just assume there are enough hydrogens attached to give each carbon 4 bonds. It's fast, it's clean, and it's basically the universal language of organic chemistry. Now, what about naming all these structures? Well, for that, there's a universal rulebook called the IUPAC system. It's a really logical method. First, you find the longest chain of carbons to get the parent name. Then you number the carbons, and finally, you identify and name any groups that are attached. The beauty of this is that it ensures any chemist anywhere on the planet will know exactly what molecule you're talking about. No confusion. Now here's a really cool part. If you think of that carbon chain as a sentence, then the functional groups are like the main verbs, the action words. These are specific little clusters of atoms, like an OH group, which tells you it's an alcohol, or a COOH group that makes something an acid. These groups are what give a molecule its unique personality, and they're usually where all the chemical action happens. Okay, so we've got a handle on what these molecules look like, but how do they actually do anything? How do they change and react with each other? Well, it all comes down to one thing, the movement of their electrons. One really important idea here is the inductive effect. Imagine you attach an atom that's super electron greedy. Chemists call this being electronegative. What it does is it permanently tugs the electrons in the bond towards itself. This creates a kind of ripple effect, a chain of tiny positive and negative charges down the line, which basically creates hotspots that are ready for a chemical reaction. Then there's another cool stabilizing force called hyperconjugation. The easiest way to think about this is like neighborly help.
Electrons from a bond next door can sort of lean over and share their cloud to help stabilize a part of the molecule that needs it, like a spot with a positive charge. It's almost like the molecule is spreading out its stress, which makes the whole thing much more stable. And this diagram really helps picture what's happening. You can see how the electrons from that carbon-hydrogen bond aren't just stuck where they are. They're what we call delocalized. They're spreading out into that empty p orbital right next door. And it's this sharing that actually lowers the molecule's energy and makes the whole structure more stable. It's a subtle thing, but it has a huge impact.
All right, picture this. You're in the lab, you've just run a reaction, and you think you've made something new and exciting. But your flask is full of, well, a mix of stuff. So the big question is, how do you get your new molecule out from all that gunk? And how do you prove what you've actually made?
Well, chemists have a whole bag of tricks for this. They've got a whole toolkit, really. They might use distillation to separate liquids based on their boiling points, or maybe crystallization to pull out a pure solid. There's even sublimation, where you turn a solid straight into a gas. Every single technique takes advantage of a unique physical property to pull that one target molecule out of the mix.
And one of the most powerful tools in that kit is chromatography. Seriously, you can think of it like a molecular race. You take your mixture and run it through a column that's packed with some kind of material. Now, different molecules will stick to that material with different strengths, so they'll travel down the column at different speeds. They end up separating into these neat little mans, and you can just collect each pure substance as it crosses the finish line. It's brilliant. So, once you've got your pure compound, the real detective work starts. To find out exactly what it's made of, chemists run what are called qualitative tests. A classic one is the Lassigne's test. You can think of it like a first-pass forensic scan to check if your molecule has other key players besides carbon and hydrogen, things like nitrogen, sulfur, or any of the halogens.
You know, when you stop and think about it, everything from the medicines that keep us healthy to the plastics and polymers that literally build our modern world, it all comes from understanding these basic principles. It all starts with the unique, amazing properties of carbon, which of course leaves us with a really exciting question. What incredible new molecule will we build next?